Welcome back to Black Hat Europe. Our program will commence shortly with some opening remarks from Jeff Moss, followed by our keynote speaker, Andrew Wang. Black Hat would not be possible without the support of so many people, especially this year as we've all been impacted by the global pandemic and have had to rethink our entire event in a virtual format. I would like to thank our sustaining partners, our global sponsors, and all of our Black Hat Europe sponsors for their ongoing support. I encourage you to connect with them in the business hall and explore the many free resources they have provided. I encourage you to attend their sessions, which are open to all attendees. To our Black Hat review boards for our trainings, briefings, and Arsenal programs, we thank you for your tireless effort in building this program. Thank you to all of our speakers for their eagerness to embrace this online format. Some housekeeping before we begin. Be sure to download your copy of Cyber Threats in Turbulent Times, a report we just published from the annual Black Hat attendee survey. The survey and report were developed by our colleagues at Dark Reading and is available for download in the Dark Reading booth in the business hall. If you would like more market research, I invite you to visit Omdia, our newly rebranded research and consulting business, who are now available in the business hall. As we kick off today's program, I would like to thank all of you for attending Black Hat this year and to remind you that the same content will be available to you on demand for 30 days in the virtual event platform. We encourage you to come back and visit the content at your own pace. It's now my pleasure to welcome back the Dark Tangent, Jeff Moss.
Welcome back. In what's only been a few minutes for me, but a full day for you, it's time to kick off day 2 of Black Hat Europe 2020 virtual event. And with day 2, we have a keynote, Andrew Bunny Huang, a prolific hardware hacker best known for his Xbox security hack. And for me, it was a very pivotal moment because when Bunny broke the Xbox, at the time, that was seen as undoable, impossible. But the moment he did it, it opened up a world of possibilities. It showed that researchers could approach some of these black box systems and really understand them. And that was what was so inspiring and kicked off a whole nother generation of hardware hackers. Now, since then, Bunny's been really busy doing a lot of things. He's been involved not only in security, but he's been involved in the open hardware space. He's been in open source software space. He's been giving talks all around the world. And one of the things I find most inspiring about Bunny is not only his involvement in open source and creating hands-on products like, say, the Chibitronics, which is a peel and stick electronic sort of crafting application, or the Chumby, which is an app-playing alarm clock. He got into things that were also very accessible for the end user, like a do-it-yourself laptop. Remember when you could sort of buy and build your own radio, or buy and build components to build your own car, change it the way you want to make it? When we got to electronics, it was really one size fits all. You get what they're selling, and you don't get to change it. And Bunny's been really trying to change that mindset by making it your hardware, where you can make the changes, and it's do it yourself, right? And that inspires a new way of thinking, more creativity. Now, Bunny got his degree from MIT in 2002. He currently lives in Singapore, where he runs a private product company called Kasagi, and he actively mentors students and startups. So you can see, he's very active in sharing his knowledge. And if you look at the history, pretty prolific in all areas of production, and I find that very inspiring. He gave this great series on YouTube, which was called Getting It Made, Stories from Shenzhen, maybe 7 years ago when it came out. And it lifted the curtain, and you could peek behind and see how hardware is being made, what it took to sort of make the sausage in China. And to me, it was really revelatory because you kind of know how things are done in the States, but once you see how it's done sort of at the street level, Bunny going door to door, figuring it out, that was really cool. Again, making the technology very approachable. Now, in Bunny's keynote today, he's going to be talking about another subject, harkening back to sort of his origin, right, towards evidence-based trust in hardware. Because you're finding, whether it's an automobile or a satellite, we're trusting this hardware more and more. And I think we need more and more eyes on the hardware to understand what's really going on. So, really looking forward to what Bunny has to say. Over to you, Bunny.
Hello, everyone, and thanks for tuning in. It's my pleasure and honor to be here talking to you at Black Hat Europe 2020, if not virtually. And I'd like to take the opportunity today to talk to you a bit about evidence-based trust for hardware, and particularly in a context of a project I've been working on for the past couple years called Precursor. So let's talk a bit about trust in a broader sense first, with the question of, do you trust your phone? And if you do, why? Or if you don't, why not? When we think about trust in the context of our gadgets and software, we have this bias that we think that maybe open is more trustable. And why do we have that bias? Is it because open source means we can read the source actually, or that we can compile our programs from source and we do that every single time we want to update our browser? The answer is no, we don't have enough time in the day to do all of that. The reason why there's a sort of a bias towards feeling that more open is more trustable is that we have evidence-based tools to transfer trust in software, things like hashing, signing, and Merkle trees. So just very quickly, hashing allows us to take a really huge file and summarize it into a short sequence of symbols, and if even a tiny change happens in that file, there's a very big change in the output sequence. And then signing allows us to go ahead and take that sequence of symbols and make it hard to tamper with. This means that if someone hands you a file, you can very easily verify that it has been tampered with and that it's actually the thing that the person meant to send to you. So in software, we can transfer trust, and it means that the place of check is near the place of use. If we were to sort of look at the overall flow for doing software, this here it sort of represents the life cycle of software development. If we start with developers, you can see these guys down here, they'll commit their code to some managed repository like Git, which has a, in the case of Git, like a Merkle tree structure to make sure people haven't tampered with commits. It's then sent to a build computer, and then someone who's trusted goes ahead and signs the binary, and that binary can be distributed widely to end users who then verify at the end of the day. And the point is that even if we have adversaries who can go ahead and tamper with, for example, the CDN, or maybe able to tamper with the build computers, we have the ability to go ahead and lock them out with these types of techniques. Furthermore, we have the ability with open source to go ahead and audit the code, to go ahead and say, okay, do we have any tampers or modifications, or do we have reproducible builds, and has anything changed since the last time we've checked? So at the end of the day, we have these tools to transfer trust and create the feeling that we have more trust in our software and in the infrastructure that we're using. Now, when talking about trust in hardware, what do we have in terms of evidence there? And it turns out that for hardware, it's actually a time of check, time of use, a talk to problem all the way down the supply chain. So, to sort of frame that, let's talk about an actual example. Let's say you, the user, and what kinds of problems you might encounter in the hardware supply chain. There's always the possibility of evil maids, but we're not going to go ahead and spend a lot of time on that. We're actually going to talk a little bit more about just everyday things like buying stuff from a distributor that comes via courier. If you go to Amazon or something and you buy it from a warehouse and it gets delivered to you, it goes to a courier, and we actually have documented evidence that some agencies, some government agencies, are able to redirect packages and put implants inside of hardware en route from the distributor to you. Even if you aren't a government agency, there's simple hacks that users can use to go ahead and get malicious wares into the supply chain. So for example, other customers can go ahead and just buy stuff in the geographic region of the distributor, go ahead and load malware into devices, and then go ahead and submit them as returns back to the warehouse. Oftentimes the warehouse doesn't actually check the returns very carefully, and they're happy to redistribute them to end customers at the end of the day, which means that you can now get implants into the supply chain. Now, people say, well, what about tamper-evident stickers, and what about sort of tamper-evident packaging? It turns out these things are bypassable. There's some good talks that have touched upon that. And if you know the right people, you can just buy tamper-evident stickers that are a reasonable facsimile of the ones that are shipped with the product. So that's sort of at the local level. But then we also have sort of the bigger problem that the supply chain goes transnational, goes overseas. So you have customs officers who by default have the ability to open packages and look at them. We have factories that are in places we don't know. And if you just cut to the chase, you go all the way back to sort of the chip design side, the product design side, all the distributors and packaging intermediate middlemen. It's a huge attack surface, and every single touch point is an opportunity for someone to go ahead and inject something into the supply chain. And so the question is, can open source save us? Can we use essentially the same techniques we use in software to go ahead and secure the supply chain? If you go ahead and you lay in, well, the position of developers on the supply chain, they're here on the left-hand side, and they drop into this big supply chain. We can have continuous integration checks. We have an open design kit. We can have open PCB designs. But the problem is, in between the developers and there's a huge amount of middlemen that the package will go through at the end of the day. There's been a lot of talk about things like trusted fabs and sort of bringing factories into sovereign territory. And I would argue that's actually only a marginal improvement, because you still have the problem of, sort of the distributor, the courier, and returns. You have individual citizens who can enter sovereign territories, order things in a territory of interest, buy them, implant them, return them to the distributors, and they may end up in the computers and hands of targets of interest. So the big problem at the end of the day is that you just can't hash hardware. You don't have a convenient, easy-to-use method to confirm the correctness of hardware before you use it. So hardware is, in fact, just one big talk-to problem all the way down the supply chain. Now, people will say, but Bunny, you once said there's always a bigger microscope. You can always look inside hardware and find the secrets. There's no such thing as hiding secrets in hardware. And this is true. There are even techniques like tychographic X-ray imaging, which are non-destructive, allow 3D imaging of very complex chips, and they're very good for reverse engineering and design verification. The problem with this is that it's literally a building-sized light source for this microscope. So if this here is a picture of the Swiss light source where the research was done, and this donut-shaped building here off to the side is literally the light bulb that's used for this type of imaging. So you're not going to go ahead and park one of these up against your house anytime soon, which means you have to go ahead and send a sample up for verification, have it come back, at which point it's gone through some hands, and you don't really have a true place of check near the place of use. The second problem is that, of course, verifying a sample is not the same as verifying the chip that you're going to use. So the proposals to go ahead and do sample verification also fail, because you wouldn't say, let's go ahead and download one copy of the browser, confirm the hash, and then never confirm the hash again after we download it. That would be ridiculous, because you would immediately introduce a bunch of talk-to problems in the situation. And so sample checking also doesn't work as well. So to sort of summarize the situation, you don't have to take it from me. There's actually a set of slides that were taken out of an NSA presentation where they said literally, who knew in 1984 that we would have Big Brother walking around our pockets, and that these are such good targets for sort of putting implants in. And this has been a problem that's weighed heavily on my mind for a while. Can we build hardware that is easier to verify? Can we, are we sort of defenseless and we don't have any ability to sort of fight this, or can we go ahead and push back against these either sort of hints or well-documented attacks that exist in the supply chain? I've kind of boiled this down into 3 principles that I have for evidence-based trust in hardware. First is that complexity is the enemy of verification. Second is that you need to verify entire systems and not just components. And third is that we need to empower end users to verify and seal their hardware. So on the top of complexity, the problem is that absent a robust hashing style function, verification falls back to bit by bit, or literally atom by atom. If you take a look at the smartphone, for example, first of all, they're held together with adhesives. So the moment you open them up, it's actually very hard to get them back together again. So the verification process itself is slightly destructive of the device. And then once you have the device apart, there's so many parts to look at, so many chips, so many attack surfaces. It would take you quite a long time to verify that it's all correctly built. There's a question actually, that was raised, like, can we actually have our cake and eat it too? Can we just firewall that complexity and sort of monitor and see if the phone's doing the right thing and not have to verify it? There's a paper I actually wrote in a research project with Ed Snowden to try and answer this question. It's about the introspection engine, and what we did is we took an iPhone 6, and we found the radio points on the inside that were used to configure the radios and sort of internally monitor the status of the radios. And we instrumented them and brought them out to a little device that you could put on the back of your phone, so you can monitor sort of the status of your radios out of band of the operating system. You didn't have to trust anything other than what was going across those signals. And so this is what the UI looks like. On the front side is the phone, and the back side is a little screen. You can sort of see where the blips are of cell phone, GPS, Wi-Fi, and Bluetooth going off. The problem is that when we put the phone into airplane mode and we thought, great, we shouldn't see any activity, we'd see blips every now and then on the cell phone and the Wi-Fi and the GPS very randomly. And we're like, oh, wow, did we find malware? Is it, what's going on? And we did a little more looking around. It turns out around the time that we were doing this research, For example, Apple had actually changed its policy that, after Mac OS 8.2 or iOS 8.2, the airplane mode doesn't turn off GPS anymore, right? So they don't guarantee that GPS is off. And, there's a lot of hypotheses for why vendors may want to do this. Like, for example, maybe they want to help build up their mapping capability. So even though they're in airplane mode, they'll still sort of do a quick scan while we aren't looking. There's arguments like, the amount of radiation that's emitted is not harmful, therefore they can do this. But at the end of the day, we have like this confounding signal of actual sanctioned vendor behavior confusing with possible malware. And at the end of the day, for us to create a filter that is capable of sort of teasing this out, we would need a lot more visibility into a lot of closed source documentation. And so this level of systemic complexity does not allow us to make a simple, clean firewall that we can say we have a high level of trust behind. So, let's think a little bit more in the simplicity direction. How simple can we get? How easy can we verify? Well, sort of the simplest microprocessor I can think of, the most verifiable one, is the Monster 6502. It's done by a friend of mine, Wendell Oskay. I love the project. And he basically took a 6502 microprocessor, an 8-bit microprocessor from the 70s, I think, and he built it out of discrete transistors on a board that's about this big. It's easy to verify. You just look at it. It actually has LEDs that light up and show you what computation is going. But the problem is it only runs at 50 kilohertz clock rate. You're not going to do a lot of modern crypto on this particular device. So let's say let's not go to that extreme. Let's bring it up into sort of say a piece of integrated silicon at a fab node that you can inspect with visible light. Visible light being 380 nanometer for a blue photon, so 500 nanometer gate width. The problem is at that node, we were only running around 100 megahertz clock rate. There was a very high power consumption for the chips. And also, they didn't have a lot of RAM. That's actually the big problem. You only have about 2.8 kilobytes per square millimeter silicon, and you become RAM bound very quickly, even if you have the compute capability in 100 megahertz. So at the end of the day, when we think about verifiable hardware, there's a trade-off we have to think about in terms of ease of verification versus features and usability. So in this diagram here on the left, I have the AirPods, and on the right, I have a conventional headset. Both of these devices do ostensibly the same thing. They allow you to talk, they allow you to listen to voice, but the one on the left has about 7 orders of magnitude more complexity than the one on the right-hand side, right? So the one on the right-hand side, the simple headphone that you put on, I can verify by just sort of with Maxwell's equations, look at the sort of the magnet on the inside and the coil of wire and the one transistor that's used to magnify the audio. I can look at and confirm that there's no implants and it's working correctly. The one on the left, I couldn't even begin to start verifying it, of course, without the source code. And furthermore, even if you could start to verify, you probably end up destroying the product and the process, taking it apart to look at all the pieces. But the main trade-off you have between the two is whether you have a cord or not, right? So they both are functionally identical, but you can make the choice of what's the convenience of having these really cool things that fit in your ear versus a thing with a little cord hanging off the side, and the orders of magnitude complexity and the difficulty of verifying them. So that's sort of a bit about sort of the complexity problem when it comes to evidence-based trust in hardware. Let's talk a bit about the reason why I say we should verify our entire systems and not just components. So if you actually look at a smartphone, and on the left is a very abstract diagram of a smartphone, you have sort of a CPU, and we already have on the inside of them secure enclaves. People are building secure chips at this point in time to go ahead and hold your private keys, which should in theory be a level up in terms of security. The problem with just having single trustable chips is what I call the secure I/O problem. The chip itself may have the keys to decrypt your data, but you still have to type data somewhere and you have to view data somehow, right? And so if you go ahead and type your plain text in on the keyboard, it's going through an untrusted CPU to route its way to the secure enclave, and likewise, the documents that come out of the secure enclave are rendered onto your screen, which may or may not be trusted. And this is really sort of highlighted by the fact that Android users may be familiar with this screen. If you install a new sort of keyboard input method, it'll actually have a little thing that pops up and says, this input method may be able to collect all the text you type, including personal data like passwords and credit card numbers. Are you okay? And pretty much you just click OK because you want that input method. It's important for you, even though you don't get a chance to verify. And what does that do to all that security inside the enclave and whatnot? You sort of just handed that really important attack surface directly over to a potential adversary. And so this is why I say it's important to verify the entire system from your fingertips to your eyes, as opposed to just looking at a single chip. And finally, I think it's important to make sure that the end users themselves are empowered to verify and seal the hardware. This is all about minimizing that gap between the time of check to the time of use. And when I say verify, I mean to empower verification at multiple levels, not just sort of at the software level or the CPU level, but sort of the design level, the gate level, the circuit board level. So all these documentation need to be available so that users can make a choice and gather evidence about the trustability of their hardware. But also, there's this sort of subtle problem in the provisioning and sealing of chips. If people have done embedded development or have had to burn eFuse keys into chips, will often find that even though they have full open source stacks to generate the cryptographic material, the final fuse burning process goes through a proprietary third-party tool or library. And it turns out it's not necessarily malfeasance that does this. It turns out the actual eFuses themselves are slightly unreliable, and there's a lot of magic that goes into making them more reliable, and the fabs and the vendors are unwilling to admit they're unreliable. They hide them behind these libraries. They don't want to share their secret sauce and technique to make them reliable. But at the end of the day, it's sort of ironic that you can put this whole stack together, and then at the final moment where you burn the keys and you're once again handing your keys back to an untrusted, unknown third-party library. So the vision is to try and create a full chain of custody of trustability from the point of generation of your cryptographic matter to the point of sealing it. I also think sealing should be physical as well. It can be physical, but I think it should be physical. It really depends on your threat model. If you really think someone might take your device and look at it, then you need to worry about physical sealing. The large number of users, you probably don't have to worry about evil-made attacks. Like I said before, if by the time someone's sending an agent to your house to go ahead and take your stuff, you've got bigger problems going on probably in your life. So this is the three principles that I've outlined for evidence-based trust in hardware. Sort of keeping things simple, look at whole systems, and making sure that we've empowered end users to verify. But the question is how do we turn these principles into actual practice? And so this is where I'm going to talk to you a bit about Precursor itself. This is the project that I've been working on for the past couple of years where I'm trying to do a case study. I'm trying to embody these principles into an actual piece of hardware that facilitates evidence-based trust. The device is simple in construction, it's open in design, and hopefully sufficient in function to do some key applications. So just to be clear, Precursor itself, as its name implies, is a development platform. It's not an end product. It's all about sort of that evidence-based trust in hardware. The potential applications you may be able to run on it are things like secure text messaging, voice chat. We've made sure it has some ability to do multilingual capability. Password management and 2FA authentication tokens are perfect for it, crypto wallets, these types of things. But because of that sort of simplicity requirement to make it verifiable, it's not going to be suitable for things like web browsing, games, or photos and videos, these types of things. So Precursor itself is made to be verified. So this is sort of a spread of all of the components that go into Precursor. We use screws, not adhesives, deliberately to make it easier for you to take it apart and put it back together again. And there's not actually a whole lot of parts when you sort of look at the spread all out. So I'm going to dig into a few of the more interesting features and talk about them. So we have a physical keyboard, and the reason, and the physical keyboards themselves are very easy to inspect. There's no silicon chips on the inside, and we handle sort of the multilingual capability by using an overlay. You can go ahead and put on top of the keyboard switch array, and you can see the overlay over here. And for example, if you don't type on a QWERTY keyboard, but you use a ZERTY or use Quartz, we will provide overlays that you just go ahead and physically put over the keyboard layout so you have your familiar keyboard that you like to use. The good news about this is that when we use a physical keyboard, the verification difficulty is trivial. So here is the actual keyboard surface itself, and you can just hold it up to the light. You can see the switches, you can see the connector, and that's it. The wires, you're done, right? We actually designed the keyboard PCB itself out of a clear material, a semi-clear material, so it's easier to do this. On the other hand, if we were to use a touch keyboard, the verification level is actually surprisingly hard because touch surfaces require a touch controller, and these touch controllers are not just simple pieces of hardware. They actually have firmware on the inside. So if you look at the data sheet of one of these touch controllers, we can see that we're at firmware version 1.x or whatever it is, and we don't even have the ability to view it. They have memories on the inside that are capable of capturing touch gestures and whatever it is, and they could be used as exfiltration mechanisms at the end of the day. We also tried to pay attention to the LCD, make sure that the LCD itself is verifiable. We've chosen a high DPI, black and white screen. It's 200 DPI and 336 by 536 pixels resolution. And you can see on the right-hand side sort of an idea of what the image looks like on it and the resolution we can get. And the reason why we picked this is that actually all of the electronics used to drive the pixels are actually built using transistors on the glass itself. And those transistors are quite large. The image on the right-hand side was taken with a sort of a common microscope you might find in a high school level science lab or something like this, a 50x zoom, optical zoom. And people who are a little bit experienced in sort of chips and circuit design will recognize these as individual logic gates that are implemented using these transistors, and these are the address decoders that eventually drive the pixel array. So it's actually, possible to verify this display non-destructively using just common microscopes. Compare this to, for example, the situation with a color LCD. Any sort of more complicated level LCD, they do have transistors on silicon to handle some pixel flipping, but they require a local frame buffer to go ahead and render images onto the screen. And so they have actually a piece of silicon, this little thin gray bar you see here, I pointed out here, it's actually a very long, thin piece of silicon that's put in the bottom that contains a frame buffer, a command interface, and all types of other things can be used to go ahead and selectively maybe capture pixels and read them out through an alternate route that you weren't expecting. So beyond sort of the input and output surfaces, we've designed our device along attack surfaces. So we thought about the whole circuit design in terms of how to delineate the attack surfaces and make it easier to verify. So this is a block diagram of the circuit board itself, and we have actually divided into an untrusted domain and a trusted domain. The untrusted domain is orange and the trusted domain is in tan. And in the untrusted domain has things that you expect. For example, we have to have a pipe to the internet, the Wi-Fi. We don't trust the Wi-Fi chip. It has blobs on the inside, just like we don't trust the cable modem or the core routers of the network. We have things like the charger and so a little bit of memory on the inside to go ahead and boot the controller of this domain. And the controller itself is a design of our own creation inside of an FPGA. That acts as a bit of a firewall to go ahead and funnel all the information into a single bus called the COM bus, which then goes into the trusted domain. And the idea is by putting all that into a single bus with a uniform specification, we can reason about the packets that are going across it. We can check for well-formedness of the packets and so forth. And I also sort of drew this diagram to think about also sort of potential side channel attacks, other ways for data to come in and out of the trusted domain, which here on the right-hand side, which as you know, contains the keyboard, the LCD, the FPGA, the memory, all the things you expect to have inside of a trusted domain. And the cool thing is now I can just kind of point to the circuit board and say, well, here are the attack surfaces. Like here are the things you should probably worry about when reasoning about the trustability of the system, right? We have a debug connector here, so that should be obviously glued shut or removed if you're worried about that. Here's the audio chip. There's a keyboard attack surface, USB and power, GPIO, and the communication bus to our sort of firewall IC up here to the north. And at the end of the day, once you've sort of inspected all these and confirm that they're sealed or have the integrity that you're looking for to your satisfaction, we provide the ability to put a single sort of metal shield over the entire trusted domain, and you can go ahead and dabble a little glue into the holes to make sure it can't come off very easily at the end of the day. So now you've gone ahead at the point of use, checked your hardware, confirmed it's okay, and then sealed it in a way that makes it more difficult to tamper with. So that's sort of talking about the input and output and sort of the large architectural features of it. But the hardest problem, of course, is how do we get evidence-based trust in our CPU? Or as I often call it, the SoC, the system on chip, because it's not just a CPU, it's a whole bunch of components that are on the chip. Now, silicon itself is something that we can go ahead and look at, but the inspection is typically destructive and hard. It's difficult to check and use the chip at the same time. So we can have these wonderful diagrams like I have here on the right-hand side, which is sort of a cut through of a chip. But you'll notice they cut through the chip. You're not going to use that chip even though you know everything about everything inside of the chip. And unfortunately, a lot of the desktop class microscopes like scanning electron microscopes and whatnot will have to do a destructive process in order to in order to sort of image all of the intermediate layers of a chip. Our solution to the problem in Precursor is to use an FPGA, a field programmable gate array. For people who aren't familiar with these, it's basically a large array of logic and wires They're user configured to implement hardware designs. This is a view of sort of a design tool view of the FPGA. We have a huge array of logic and wires. You can see the actual devices themselves, and we can sort of see how they're wired together and what the logical mapping of all those devices are. And the key idea is that the FPGA allows you to compile your own CPU, thereby narrowing that time of check to time of use gap. So by giving people source code, which in this case is in Python, allowing them to compile it down into sort of an intermediate Verilog format that's then turned into a bit stream that is loaded into the FPGA hardware itself, we allow things like signatures so other people can do the compilation for us, and all I have to do is confirm that the bit stream matches the bit stream that someone else has put the effort in to check and verify. Another really cool thing that we have with an FPGA is we have a technique they call sort of ASLR for hardware. So ASLR is address space layout randomization. I'm pretty sure everyone in the Black Hat audience is familiar with this. It's, you know, when you go ahead and you change the location of various object files at link time to make sure that when you have a stack smash, you don't have a very easy time of locating, you know, gadgets and whatnot for your attacks. You can do something similar like this with an FPGA and hardware. Since you have a big array of logic that is essentially randomly mapped to your design, you can recompile your design with some random seeds to go ahead and change that mapping. So that way, no one can go ahead and sort of prefab a chip with a couple logic cells with implants on the inside to pull bits out, because you don't know where your program counter is going to end up. You don't know where the instruction decoder is going to end up when you can go ahead and recompile the chip for a new piece of hardware. And what that means at the end of the day is that you know, you can't just backdoor an FPGA by putting a little bit of logic inside every single one of these logic gates, because it would just blow up the area of the FPGA. It would become a much larger chip in and of itself. The sort of thing you don't need a high-end microscope to reveal. You can just see it in a regular X-ray scan. You'd see that the chip itself is much larger than you expect. You'd say, wait, someone maybe has gone and backdoored all the logic gates. Instead, you're reduced to now trying to sample or some other kind of thing, but it's not as effective. It's an interesting mitigation that we get with FPGAs. And then finally, you know, there's a question of, you know, what is in that bit stream that comes out of the compiler? Do we know what's on the inside? There are some projects that are ongoing right now. For example, PRJ X-ray, you can see the GitHub repo for it on the lower right-hand side, where they're going ahead and they're actually fuzzing the bitstream generators to discover the meaning of every single bit in that bitstream. So now we can actually say, what does this bit do? Is this bit actually doing what we think it should do? And if something changes in the bitstream that you've never seen change before, is that legitimate, or is that something we should worry about? So we have the ability to sort of partially mitigate tainted tool chains, and also the ability to introspect into the bit streams and confirm that they're doing something correct. So the big picture about FPGAs is that FPGAs allow us to move the point of check closer to the end user. And the vision, we're not there yet, but the vision that I would like us to get to is that we just have a one-click tool that allows users to sort of compile and verify their FPGA bitstream. And that really means that we're bringing ourselves to the point where the point of check is exactly equal to the point of use. So let's take a quick poke inside the FPGA and see what's inside of it. So this here is a bit of a big diagram that I've drawn up, but it shows you all the sort of things that are inside of our current proposed SoC for Precursor, and it changes all the time because it's an FPGA. We're allowed to update it, we're allowed to change it, which is actually kind of cool. I'm not going to go through all the individual sub-blocks, but I'll talk through a couple that I think they're probably most interesting to the people watching this. First of all, the core complex. This is where the CPU is located. We use a single core RISC-V CPU. We're using the RV32 iMac instruction subset with an MMU. And this is actually a little bit unusual to have an MMU in a small embedded device. It's normal for phones and servers, but we insisted on having an MMU in our hardware configuration because, you know, we know how to do memory protection. Why don't we use it in our embedded devices? Even though we don't need it for paging and virtual memory, it's great for memory protection. And we're using an implementation of the CPU called VexRISC-V. The VexRISC-V actually itself, of course, is open source. There's a GitHub repo for it. It was actually developed in Vex, Switzerland by a guy named Charles Papadon. It's written in Spinal HDL/Scala, and it's cool. You can actually, you know, go to the source and look at all the opcodes that have been defined in this particular CPU implementation. So the question of, you know, are there hidden opcodes is no longer an exercise of fuzzing and throwing all kinds of opcodes and seeing how the CPU behaves. You can actually look at the source and understand what's going on the inside. Another sort of significant thing that I really enjoyed about having this open source approach to the CPU is that we can patch it, right? So just a couple weeks ago, the maintainer had sent me, Charles had sent me an email saying, oh, I found a problem. There's a CSR plugin privilege crossing issue that will allow sort of privilege escalation on certain operations. On a closed source CPU that's fabbed in silicon, this would be like a named exploit. It'd be like one of the zombie load or Spectre level types of things. You have a logo and a website, and be giving Black Hat talks about it, whatever it is. On an open source CPU, it's just a commit and a patch. At the end of the day, we just found a problem, we patched it. It's not a big deal. We can go ahead and push an update out. And this is a really powerful sort of aspect that I look forward to working with. And as we sort of validate Precursor with the community, find more issues, we can go ahead and repair our CPUs and not be stuck with sort of unsavory decisions. Which brings us to issues like Spectre. So Spectre is a side channel attack against CPUs, and it takes advantage of the fact that there is microarchitectural state that can leak information about the execution status of the CPU based upon a timing side channel, right? And so sort of the status quo right now is in order to mitigate that, we have to disable these optimizations. We don't use them anymore, or we find a way around them because we don't want to have that timing side channel. Well, the cool thing is that when we have like the ability to do microarchitectural analysis on the source code, we may actually be able to do those optimizations. The compiler maybe will reason through the code pass, maybe reason through the optimizations, and guarantee that there are no timing side channels that are of issue, but we can still have the optimizations in areas which are not timing critical. So I think that's a potential thing that we might be able to look forward to with this more open approach to SoC and CPU design. I'd like to give a quick shout out actually to LIDEX. LIDEX is a powerful system on chip integration framework, and this is what we're using to sort of put together the whole chip itself. So in addition to all these components, we have to have a way to glue them together. It's developed in France by a fellow named Florent Camarec, and you can see his GitHub repo over here. As I mentioned before, I alluded to the actual SoC is written in Python. It doesn't mean that we're executing Python to emulate it. We actually use Python to sort of describe an intermediate language called Verilog that we then compile into a bit stream that is then loaded onto the chip. It's really cool in that none of these decisions I made are actually locked in. If you get the device and you say, oh, I don't want to use this particular RISC-V core, there's several RISC-V implementations you can pick from. You can use PowerPC, you can use LM32 or 1K, and it's all changeable by just changing out a couple strings in the description of the SoC and recompile. Of course, you have to deal with the software problem, but you can go ahead and change out the hardware quite easily, which is actually a bit inverse from the usual situation. And finally, I kind of want to point at the Cryptography Complex. That's another thing that might be of interest. We've gone ahead and built in accelerators for common protocols, things like AES, SHA-512, SHA-2, Curve 25519 operations. Those all have dedicated hardware accelerators. And this helps compensate for the relative speed of the CPU, which is only at 100 megahertz right now because we're running in FPGA. We also feature a key storage ROM, and the reason why it's a specific individual block is we do a trick where we hard locate it inside the bit stream itself. And because we have the ability to introspect in the bit stream, it means that when we generate new keys, we can edit the bit stream of the FPGA itself, reload the FPGA, and have that inside of our device without using any third-party tools, without using any sort of these burning utilities to go ahead and get the bit stream into the end user provision device. And that's a very important priority for the project. We also have a random number generator. We have one actually internal to the FPGA. We also pair it up with one external to device. We use this complementary approach because the internal ring oscillator is a little harder to verify. You can go ahead and bypass it and bring it to a pin and then say, okay, I'm done verifying it. Let's plug it back into the device. But you never know if actually it's been plugged in or not, or if it's been swapped out with something that's more deterministic. But the good news is that this ring oscillator inside the chip is a bit harder to tamper with, right? You have to actually get past the epoxy of chip and attack the silicon itself. We also offer an external random number generator that's built a little avalanche generator on the outside, which is actually trivial to verify. You can put an oscilloscope on it and verify that the avalanche diode is doing its thing. But the problem is it's also easier to tamper with, because if you can get a hold of the hardware or maybe expose the user to high levels of radiation while they're using it, you can go ahead and maybe disturb the operation of the device more easily than the on-chip one. So we provide both to give some defense and depth against different attack scenarios. And finally, we have some tie downs for internal debug buses. So it's always important to sort of take a look at all of the pieces of hardware that may be laying around that you're not using that could leak information. So we did a quick audit and we tie down the blocks that we think are going to cause us a problem at the end of the day. So that's sort of the nickel tour of Precursor. It's all about sort of enabling evidence-based trust, and we embody the three principles I talked about, sort of complexity as the enemy of verification. So we build a device that hopefully is adequately simple that we can verify it. We want you to verify entire systems and not just components. And so, the Precursor device itself, as you can see, is end-to-end from your fingertips to your eyes in terms of maintaining custody of your secure information and getting it to the human user itself. And finally, we empower end users to verify and seal their hardware by making it open source, by providing tooling, by providing documentation at the end of the day. So the whole concept, backing out into the big picture again, is that Precursor allows us to close that hardware time of check to time of use gap. So we have, again, this scenario where we may have this whole supply chain, a lot of actors that are maybe acting with or against our interest. But the idea is that now we enable you at the time of use, right, to go ahead and take apart the device and look at it. And part of the idea of making it so open and more simple is that even if you don't have the individual technical know-how to inspect the circuit traces or to look at an FPGA and know what's going on, the idea is to have it within 1 or 2 degrees of separation in your personal social network of someone you can consult that you trust to get an opinion on this, which is different from going to, for example, a third-party certification agency who you know nothing about. It's just a government agency or wherever it is that will go ahead and say, sure, trust us, this thing is secure. We don't know what their values are, what their agenda is at the end of the day. The idea is that you pick the authorities that you want, the people you want to trust to go ahead and do the analysis. And ideally, we make it open enough that within a couple of degrees of separation in your network, you can go ahead and sort of create your own evidence-based trust case for the piece of hardware that you're going to use. So here's the current status of Precursor itself. I've talked a bit about what it is, but here's where we are today. Right now we have hardware. We're at a crowdfunding stage actually right now, so it's near final. And if you go to precursor.dev, it'll direct you to our crowdfunding site. You can check out all the details about what it is and whatnot there. The software itself is running in OS called Zeus. It's by Sean Zobs-Cross, and he's got it booting. We've got messages passing. We've got memory protection going. We're just starting to explore the UX and application side of thing. We're looking for developers. So if you're interested, go ahead and check out the campaign, and also you can look at our GitHub repo and look at the Zeus core repository. We have an actual emulator that runs on a technology called Renode, where you don't have to own the hardware itself to go and start writing code for it. You can actually start in an emulated environment and start poking around and seeing what you can do with it. And finally, I wanted to give a shout out to NLNet for funding. We got a grant through NGI 0 for privacy and trust enhancing technologies. Without sort of their sponsorship, we would have had to sort of go to crowdfunding a lot sooner, and we wouldn't have been able to be as thorough or as put as much effort into the documentation because we'd be worrying about, sort of covering tooling costs and stuff all the time. And so a really big thanks to them for making this possible and allowing us to do this research and to share it with the community as a whole. And with that, I'd like to turn it over to the Q&A. Thank you everyone for your attention, and look forward to seeing you guys online.